Well, thank you very much for having us over as sponsors. It's my pleasure to discover this meetup and this amazing community. This is our first opportunity to speak here and sponsor it, and hopefully going forward we'll be doing more things together. My name is Victoria Lifshitz. I'm a founder and these days CTO of Grid Dynamics. For those of you who never heard about us before, we're now 10, almost 11-year-old company. I've started the company back in 2006. And I was coming out of 10 year at Sun Microsystems, where I generally focused on massively distributed systems and next generation architectures. And the term cloud has not been coined yet, right? The term Devops have not been coined yet. MapReduce has not been coined yet. Hadoop has not been coined yet. But there were clearly these new software architectures that were emerging, that were massively distributed, that were in memory, that were NoSQL, that we called computing Google style, and we called it horizontally scalable. There were no vernacular, industry vernacular for that yet, but it was clearly that it weren't your, mother's three-tier enterprise systems where everything was starting and ending with Oracle database and with a little front end in between. It was also clear that cycle time starting to matter, not computer cycle times, but developer cycle times. Amazon was already running circles around much more established retailers because they would out-innovate everybody. And even back then, Amazon could release software so much faster than anybody else. And Agile was starting to take hold, and people were starting, even big enterprises, starting to get, at least somewhat curious, if not yet serious, about shortening software development cycles. Back at those times, major software upgrades were every 2 years, right? And a minor every 6 months. Waterfall ruled, but me and a bunch of people that I work with, we were all experimenting with a lot more lighter ways of writing software services and iterating quickly and deploying and testing automatically. So these are some of the things that I've been sort of doing at Sun, way predating its mainstream times. And on top of that, the last thing that I actually formally did for Sun was I was drafted to be the architect for a very first public cloud service offering. It was called SunGrid. It launched in 2004, predating Amazon by a couple of years. It pioneered this model of selling computers $1 per CPU per hour. If somebody has been in the valley long enough, you guys might remember. So I had a chance to work on this project. I was the architect for what was called developer utility. And the developer utility, the idea was there is a production utility and developer utility, and developers develop and test their software on your developer cloud. Cloud wasn't called a developer utility, and then you promote it to a production utility. It was an amazing collection of ideas, and I was completely sold that basically virtualization meets the internet, meets the capacity on demand, meets the cloud computing is sort of the way of the future. But boy, oh boy, were we struggling to get applications to deploy on our platform. None of the modern software stack, none of the things that companies were actually running could in any reasonable way to be deployed on this thing. So Amazon, of course, had a strike of brilliance to go after little PHP code and greenfield applications. Sun's idea of a pilot of SunGrid was to sign up, I think it was one of the giant financial services corporations for 6,000 node cluster was the idea of a pilot. No wonder that didn't work out and didn't take off. However, working on that stuff made me convinced that the future is really kind of confluence of three things. Evolution of infrastructure towards the clouds, where infrastructure will be dynamic and it will be flexible and will be charged per hour, and it will be sort of all you can eat, all you need to eat, and pay for only what you've ate, kind of a thing. Evolution of software architectures towards lightweight, massively scalable, in memory, NoSQL, largely written with open source technologies, because open source technologies were starting to make its way, and commercial vendors had zero interest to try to figure out actually how to make it work. And the third was the agile development and what today we know as Devops, automation, because without automation, you really could not either control dynamic fluid capacity or the software architecture stacks that now had to be composed of little tiny pieces of software. Anyhow, 2006 rolled by, and I thought this future of cloud computing will be incredibly interesting, and I wanted to create a company that would essentially focus on helping enterprises make a transition to that world. And I thought there will be a lot of customers will be interested in that help, and they will need a lot of help. That I proved to be right. And so that was kind of the genesis of the company. Now, for the last 10 years, this is basically what we've been doing. We've been taking companies on the cloud when it is open source stacks, running in a mission critical type of massively scalable sort of problems, running on the clouds and with high degree automation. Now, with that territory, sort of a big data processing, transaction processing, real-time processing comes with the territory, because these tend to be the kinds of systems that we focus on. The very, very first customer of ours was PayPal back in 2006, who wanted to do fraud detection in real time, in memory, in sort of a private cloud, as opposed to big hunking Oracle system in which they were sitting on today. That's kind of the genesis of the company. And over the years, we had a fun and privilege to build big pieces of, Mesos.coms, Coles.coms, work with Microsoft, Cisco, Yahoo, and some of the other really, really cool companies helping them build bits and pieces of a cloud infrastructure. That's a little bit about us. Now, this is probably a very, very technical meetup. And I want to say right away that there used to be a time when I was actually a genuine engineer. This time, I'm a CTO, I'm a suit. I take credit for the work that real engineers do. So I might be a bit at the high level when you ask your questions, and I hope that you do, that go below something that I can answer myself. I have one of my engineers, Sergey, here, who are responsible for the DevOps piece of some of the things that I'll be talking about and showing. So when it comes to the deployment and DevOps, Sergey hopefully will be able to help me. I don't, unfortunately, have my colleagues who did more of the application architecture stuff. They are not even on this time zone. They're not even in this country. But anyways, we'll do the best to support your questions. If I can't answer something, I'll take it offline and follow up. OK? So I'll kind of start afar, and I'll start talking about, well, what is real time anyways? And real times can mean different things to different people. We look at it from a business application prism, and mostly focus on, well, where are big companies really spending big budgets on the new programs that have need of real-timeness? And the way I think about it is that, fundamentally, there is an event coming in. And there will be a response to this event. And we somehow want to control this event response cycle. Now, a lot of interesting things happen in between event coming in and response being formulated. One, we need to capture the event. We need to register that the event actually has occurred. Second, when event occurs, it actually augments our model of the world, because our model of the world is based on data points of everything that happened up to this point. But now a new thing has happened, right? So we actually need to go and augment our model of the world. So that's the learning piece. Well, then we want to apply our understanding of the world through whatever models we have to then analyze that event and come up with what do we want to do about it, some kind of a course of actions. And then we need to deliver that course of action, right? And here you have a response. So when we talk about real-timeness, the real questions to ask is, well, how long is the cycle? And which part of it is actually happening online versus which parts of it are happening offline? And of course, we are forever fighting for faster, shorter, better, right? So one way to try to categorize what real-time means in analytics, in machine learning, in data sciences, in AI, I kind of have this simple 3-level pyramid. The simplest thing that you can do, and this is, I think, by and large, where state of the industry is today, is that in real time, in line, you are responding to event. So event response happens in real time through some kind of online systems. But that's based on some kind of rules. But the rules are really devised offline. So the whole training learning cycle, as well as analytics cycle, it happens at best the night before, and then the results were delivered to online systems. Sometimes it can take a lot longer than a day. to accumulate the latest results and then incorporate them into your new models. I'm going backwards. I need to be going forwards. OK. So the next logical step forward, and this is where stream processing engines come in, is we could do better than just respond to the event by the basically predefined, pre-qualified rules. We can actually do analytics itself right in real time. As the events are coming in, as the events occurred, right, we want to grab them and we want to analyze them and we want to figure out what it is that we want to do. Learning, however, still happens offline. And the Holy Grail, Nirvana, the place where we all want to get to, is actually sort of the third step. In stream processing technologies can get you there for some limited set of algorithms, probably not for all, because some computational problems simply don't lend itself to that degree of real timeness, at least not yet. But essentially, we want to do all three things, including learning right on the fly, right? So that's kind of the world of business value with respect to real timeness. I gave a talk a little earlier today where I focus more on kind of a business set of problems and rationalize type of business use cases and how some of them can be done with offline analytics, but some absolutely require online analytics. I'm just going to fast forward that part for more technical crowd and just briefly outline what we see today in 2017 being some of the biggest budget drivers that our customers, and a lot of them are large retailers, are allocating towards essentially real-time type of problems. And I'll start sort of reversed order. Number 6, the most obvious one, and the one that people had been using real-time system forever, are various types of alerts. Anything that is an anomaly from a normal pattern, you want to pick up and then flag and then respond. It starts with things like, of course, fraud detection. How do we know that something fishy is going on? Can you effectively monitor normal transaction flow and pick up just the ones that look odd? Surge in demand. And more clever and interesting things are related to trends or changes in weather. Can you detect those things? And if you detected those things, can you actually respond to them in any kind of interesting commercial sense? Or I will be later on showing how these systems can be used for real-time sentiment analytics. That's our Hello World demo, if you will, of the basic science kitchen that occurs for these kinds of systems. So you might want to catch the fact that public sentiments towards your brand all of a sudden suddenly shifted. Something has happened. You probably want to be alerted about this right away and figure out how to deal with it. Next is intelligent sourcing. Intelligent sourcing is a problem that a lot of retailers are starting to pick up. And that's the one that traditional technologies don't really offer a very good solution for. This is the one where, imagine that you are a major retailer, I don't know, Mesos or Kohl's. It's Black Friday. You're consuming orders at the rate of thousands, right, per hour. And you have a very complex optimizational problem to solve, which is as orders coming in and a customer is buying these 10 things, where do you ship the items from? If you do it in a silly way, and you put these 2 lines from this store and these 3 lines from this store and this 4 from that one, you're going to get absolutely killed on shipping costs, right? Your margins is going to be done. Amazon is brilliant at this, best in the industry. Everybody else sucks. And so people used to use systems that are working just fine on a much smaller scale. But with the shift more and more towards internet buying and kind of a consolidated problem of aggregated number of offers plus the number of locations, fewer and fewer retail points becomes warehouses. So now if you used to have 3 distribution centers, now you have 700 because you can ship any item from any store. All of a sudden, computationally, you can't really solve that problem the way you used to before. So you need to do this in real time, because you cannot really offload this thing. If you solve this well, you can actually start doing even smarter things, like if a customer picks some big expensive item and he's still shopping, show them only products that you can actually fulfill from the same place, right? There's actually, it might sounds to the engineers like really boring business stuff, but that is a really, really hard business problems to solve with some very advanced technologies needed. So anyways, intelligent sourcing is a second class, general class of problems. Dynamic inventory management. So this is the one where we are looking at the entire supply chain, and we are trying to predict where your bottlenecks are. And if one store overstacks the supplies and the other understacks, you have incredible inefficiencies. More and more, you could do this thing on demand, and you could do it in real time, and you can reshuffle inventory, right, between your various stores and locations. But again, in order to do that, you need to do a lot of real-time, both sensory and decision-making. Dynamic pricing. Dynamic pricing is up and coming, and dynamic pricing is essentially determining a price of an item, either price of an item or the amount of discount that you're willing to give consumer who is right now buying this item, depending on a whole lot of dynamic parameters. Not only how much it's supposed to cost and what do you know about the customer and your guess as to what is the right price where you can close the deal with that guy or gal right now, and what is other competitors charging for it, and what is my total supply availability. So these kinds of things, again, are presenting very interesting business challenges that should be solved in real time. And you cannot solve it with traditional architectures. Personalized offers, and our absolutely favorite is the personalized search. We as a company do a lot of work in high-profile retail search engines. That's actually one of our specialties. We build some of the largest search engines for large item catalogs that have 100,000 to maybe million plus UPCs in a catalog, which take care of assetization and real-time availability. So this kinds of stuff is our home turf. And if you know how search engines work, it's about identifying the right fit with the right objects and then ranking them, determining relevance. And all the rage is now doing all of this dynamically and doing it completely personalized, using machine learning, and two different people searching for exactly the same phrase at exactly the same time are going to get completely different answers depending on who they are. So these are some of the set of business applications that we see very rapidly emerging, which require these kinds of architectures at a truly mission-critical scale. And it is to address largely these types of domains. We see the emerging platform of real-time analytics, of generally stream processing, or what I like to call in-stream processing, is designed to address. And one of the definite themes that I picked up at this Strata Hadoop world is everybody, it seems to be all the rage. Everybody is in streaming. Everybody is speaking and promoting real time, right? So this is, having done this now for close to 11 years, it's very gratifying to see it moving from early adopters and fringes to kind of very, very, very mainstream. Where does stream processing, if you will, fit? Well, how you manage data in the enterprise is a really, really complex landscape, right? And looking at it end to end, you have systems that collect the data that are generated by increasingly world of IoT. And you have data coming from a variety of backend systems. And you have batch processing and ETLs that collect that data sort of in mass and then transport them and transform them and index them and store them. Then you have the data lakes themselves. And then you have traditional BI and the new emerging world of data sciences. And then we tend to use it in two broad classes of applications. One are customer-facing, for online applications, and one for a back-end things that are about technical support and first response, these types of systems. Stream processing is really about this one piece. It's about how do you build real-time extensions, right, on top of that big data landscape, if you will. And one part of it is the actual stream processing, that's real-timeness, and part of it, of course, inseparable is how do you actually do data sciences, how do you actually do modeling and learning so that that stuff can work. Does that make sense? Any questions so far? Okay. So stream processing, of course, is quickly becoming mainstream, growing rapidly across multiple industries. This is just a quick snapshot subset of some of the by now almost classic applications of stream processing. But for a lot of companies, the journey really is from offline analytics to online analytics, right? A lot of companies do have Hadoop infrastructures. They do have data lakes, and they do have an awful lot of ATLs that I've already put in place over the last 5 years. And they are doing things offline. So for the companies who are doing things offline, often the conversation about stream processing or real-timeness is, well, where does it come in and what it can be do better than what you already have today? And generally, we see sort of 4 big classes of problems that are well solved by adding stream processing on top of your existing big data landscape. One is real-time data ingress to essentially replace batch processing wherever possible. If you can catch event at the source, just as it happens, a bunch of it is coming from Internet of Things, but it could also be coming from other enterprise feeding systems. Just don't get it as a batch at the end. Get it right, maybe take it right from the message bus, because sooner or later, often these events are somehow disseminated from message buses. So don't wait, grab it right away. And then at least in your data lake, the data will always be fresh and up to the minute, and you could do your classic traditional reporting, but at least you're not waiting hours to get the data. It's always fresh, it's always there. The second large class of problems I generally call the problem of filtering or identification of actionable insight. And actionable insights are these things that are really 1 in a million. If you think about it, most of the events are uninteresting. You have a beacon that is sitting there and just reading the reads, right? And reading the reads. And only very infrequently something interesting happens that you want to pick up and say, I actually want to do something about this. So you need a very efficient means by which you can filter out all the noise from the signal and identify where is the signal. Signal is the actionable insight. Stream processing systems are very good for that. And then, of course, once you know that something is interesting, you can do one of 2 things. You can either farm that interesting event back to some kind of a line of business system that can take care of it, or you could just take care of it right there and now, right? So you can add then response to actionable insight right in line as soon as you identify the insight. And finally, sort of the last frontier in some sense in that pyramid of value is then starting to learn in real time and augment your models as new events occur. And sort of looking at the vendor landscape, if you will, this is the build versus buy tree. For companies who like to buy big vendor products, there is plenty of products on the market and growing very fast. Anybody who is in the Hadoop big data space either already have stream processing capabilities or adding them in a hurry. So there's a ton of products that you could choose from in that branch. But more and more companies, and those really are our customers, and I suspect most of engineers are in this meetup is probably more in the second camp. And that is, we want to build this system, but we want to build it from open components. And if you are on that train, then there is another big decision tree coming up. And I think that decision tree, a lot of people are actually not yet cognizant that they're making. They're almost making them as emergent behavior. And that is, do you want to bet on the cloud or do you want to bet on open source? And what I mean by that is that what I think most people want is they want open source componentry running on a cloud. But what's primary? And if you pick your cloud platform first, then you're presented with a plethora of APIs that cloud vendors put in front of you. And since stream processing drives a lot of computing cycles, there is clearly a war going on and will be continued to hit between Amazon, Google, Azure, and other Google players in terms of offering developers better set of APIs. Well, once you pick one of the set of APIs, you're locked in, just like you would in any other platform, to a large extent. Now, the winner is stay open with your APIs, get the best cloud offering that you can, right? And so, that train of thought gets you to open source comes first, cloud choice comes second. And thankfully, we have an incredibly vibrant ecosystem of components that allow you to build this system. Where grid dynamics comes into play? Well, we're a services company, so we don't have any products. What we do is we do an awful lot of complex implementations. And when we do, what we walk away with in our IP is really the best practices and the blueprints. We learned something by doing that. And then as a CTO of Grid Dynamics, one of my missions and really sort of the underpinning of our marketing programs is let's take the lessons learned from these implementations, let's codify them in blueprints that essentially abstract the reusable part that says this technology stack shows itself really well to solve this set of business problems. Well, let's pre-integrate it together, let's document it, and let's open source it, and let's put it out there in the community for people to use. That's really what we do, what I do, my CTO office for Grid Dynamics, that's what we do. So I call them blueprints. And what I'm going to present to you today is essentially this kind of the open blueprint for stream processing. OK? Make sense? OK, so without further ado, this is a result of the work of a very small team that works for me at Grid Dynamics. And again, this is not so much in any kind of a new innovation as it is capturing of something that we know works in the field because we implemented a number of systems with these components. And so we asked the question, if somebody wanted to start a new stream processing project, and it's a fairly general purpose stream processor, can we come up with a standard reference architecture and reference implementation? That would be maybe 50%, maybe 70%, maybe 75% there. And then people can introduce their own specific modifications on top of that. That's really the intent. We want it to be pre-integrated. We want it to be cloud ready. But in addition to that, we also want it to be cloud portable. So that cloud is a customer choice. And not only that, but the cloud choice could be changed by the customer, basically at will. And that's something that happens awful lot with our customers as well. Just very recently, we did a major project. We launched a new search engine for a very, very large retailer. It was a 6 months effort, which is actually fast for software of that complexity. And it went as a cloud service. But the customer changed their opinion what cloud they want to launch it in 3 times in the course of a project. And last time, it happened only a few weeks before going live. And because we invest very heavily in the layer of essentially isolation of application architecture from the underlying infrastructure, we were able to recertify yet another choice of a cloud within 2 weeks. That's actually really hard to do. And there is a real business value behind it. So I'll be showing you a little bit today, what we do to achieve that. And then we want all pieces to be basically free. And then our blueprints are free as well. Now, every software architecture has to solve some kind of a bounded load problem. Every time you change the scaling factor to 10x, you usually have to completely rewrite the architecture, right? So this one is designed to be pretty darn good and suitable for pretty darn wide range of use cases, probably not all of them. Several years ago, we had an opportunity to work with Yahoo, particularly on deploying and automating some of the testing and management of their Yahoo clusters, which at the time were the largest in the world. And they were capturing some completely incredible amount of data. And architecture like that would not work for them. But they were the largest computing thing of its time, right? So this is suitable for normal range, I would say, of business applications, somewhere between 100,000 and maybe million events per second. That's more than that. You're really, really pushing it, but that's a lot. Latency, about seconds to really compute the actionable insight and what you want to do with it, and about minutes to then deliver it to whatever is the end receiver of that system, right? Pretty good reliability on commodity type of infrastructure. And generally, streaming systems look something like this. You have events coming in, so you have some kind of a messaging service that is catching the events. And then you have some kind of a streaming framework that is processing the events. And then we're discovering that you actually need 2 types of operational stores. One is more or less very fast, lightweight, in memory for reference data. And one for much more complex data structures that might be holding application state or intermediate results or something like that. And then you need to be able to deliver the results at the end to the downstream systems in a variety of different ways. So this is a general purpose architecture of, I think, any in-stream processing system. Ours made some choices. That's the value of the blueprint, right? We made some choices. So our choices is for queuing, we use Kafka For stream processing, we use Spark Streaming. For lookup store, we use Redis. And for operational store, we use Cassandra. Now, this all tends to sit on top of, often, it could stay either standalone as a cloud service that is separate from any kind of a big data infrastructure, or it can sit on top of the existing Hadoop infrastructure. And then the resulting insights can either really be delivered as a set of APIs, or integrated with the HDFS, or some other means. Hopefully this makes sense. This is probably pretty close to what people would do today. Interestingly enough, when we started doing things like that, Kafka wasn't around, so queuing mechanisms were different. We did a lot of work in early days with Storm. So actually early field implementations were more Storm-based, and then Spark came along. And it's not that Storm is worse or inferior, but we looked at where the biggest usage is, and there seems to be a much more vibrant community around Spark Streaming. So that's really one of the main reasons why we picked that. One of the important things to think about is that once that system creates the insights, what are you going to do with them? Right? And it has to support different modalities of doing something with it. And in this case, the critical insights could be exposed to other business app on demand, essentially through some kind of a REST APIs, right? Come and get it. It could be delivered to other systems through REST APIs, so our system can go and call them and say, here you go. Or it could be pumping data back in another message queue, which others then pick out of, or it can be ingressed into some other data store. Now, it's one thing to pick up components because they functionally do the job, and it's a whole different set of questions of how do you actually now make the entire blueprint work as a platform. And what does it mean to work as a platform? It means that the whole thing should have no single points of failure. It should have automatic failover. It should have automatic data or some sort of a data replication. And you're coordinating a lot of things. You're coordinating things that are clustered in very different ways. Kafka clusters one way, Cassandra clusters another way, Spark clusters third way, right? Redis clusters yet another way. But you need to put all of these pieces together so that you have the operational blueprint. Frankly, a lot of value of what we do and the blueprints are really on that side. Because components, again, you can replace Spark Streaming with Storm, but there will be implications on operationalization of that blueprint, right? And so when all is said and done, and I'm not diving into these details today unless you guys have specific questions, and then I'm happy to try. The point is to say, these are the things that we do, and there's a whole lot of details of why this choice and how it works underneath on our blog. We have a whole series of blogs dedicated to documenting these architectures and the series of choices made behind it. At the end, what we want is not a collection of software components, but the entire system that is designed to be a platform that you can take wholesale and basically start as a baseline, start building your systems on top of it. We want it to also be operationally ready, right? So it comes fully Dockerized, containerized, Dockerized. It comes, in this case, with bindings to Mesos and Marathon. We'll talk a little more about it in the next section. We are thinking about doing reference architecture with Kubernetes. And maybe native Docker ecosystem. As these technologies mature, if you will, that's definitely, and we do quite a bit of work with Kubernetes, so Kubernetes is almost no-brainer at this point in time as the alternative deployment blueprint. Now, to make it all work, we issue reference implementation. And the reference implementation now is literally a set of scripts and buttons that you can press that allow you to take this whole multi-cluster thing and then deploy it on the cloud and actually see how it works in reality. And then again, start with that as your deployment platform. And to illustrate and how would somebody use it for data sciences, then we have a reference demo. That's a real-time Twitter sentiment analytics for new movie reviews that is deployed and running inside of that in-stream processing system and helps you understand, what goes where and where do you put the models and where do you put the analytics and how do you collect and visualize results and so forth. And so with that in mind, let me talk a little bit about now the reference implementation. And again, if reference architecture is more about software stack, then reference implementation is about DevOps stack and how to automate all major functions related to management of your platform. So this is a chosen DevOps stack for a reference implementation. The choice of a cloud is AWS for no good reason other than we had to choose one, and so that one was chosen. I'll tell you in a second what it takes to deploy it on any cloud, and you'll see that tie-in to any kind of cloud is extremely minimal. The deployment unit is a Docker container. The container management is the Mesos and Marathon. Why Mesos and Marathon versus Kubernetes? We actually go to some length discussing that on our blog, mostly because when those choices were made about a year ago, Mesos Marathon seemed to be much more mature and widely used in the industry, and Kubernetes was kind of, new kid on the block, up and coming. We are considering the revision of this blueprint sometime this year. We would very likely to do it with Kubernetes this time around, but we'll see. There is a two-step to deployment process. One is kind of the bootstrapping from what I would call bare cloud infrastructure. A set of VMs is all you get from the cloud. Now that's all you've got to get going. So we use Ansibles to get the first step of bootstrapping as automated as possible. From that point on, once you grab a certain number of VMs and kind of put the brains of operation in, now you can automate the rest. And that includes a lot of orchestration, application management. That we use one tool that you guys probably have never heard of. It's called Tonomi. We're using it today. It's actually a tool and technology made inside Grid Dynamics. So it's our own proprietary IP. It's a company that Grid Dynamics acquired. We are in the process of a little bit of a soul searching. Either we will open source that for a greater of the community, or we'll port this blueprint on another alternative, fully open source implementation, so that we have it as we promise, end-to-end open source. So how do you achieve cloud portability with something as complex as deploying Cassandra here, Spark here, Kafka over there, and HDFS in between? Well, it kind of boils down to very cleanly separating kind of two phases. The bootstrapping phase from the normal application environment management space. And the bootstrapping goes something like this. Step number one, and that's one manual thing that you need to do, and that is you have to choose a cloud. You sort of can't have a robot do that for you. And once you chose the cloud, you have to go and get, using whatever cloud means are available to you, first set of VMs where you're going to install your brains. So that piece of manual. After that, we actually provide you an automated Ansible scripts to grab that set of VMs and then deploy and configure Mesos Marathon cluster. And now you've got your brains. Now, once you get the brains, now you can go to phase two, and that piece could be completely automated. And that's use basically then that management cluster to provision the rest of ISP environment. And first thing you need to do is you need to bring a bunch of different components as containers. And then you need to deploy applications. For example, one of the applications that I'll be showing uses external Twitter connections and Twitter APIs, right? So if you need to provision that, you go provision that. And some of these things could be standalone services that need to be provisioned alongside with your ISP infrastructure. Then you need to go configure all the dependencies. And after that, do fun things like scale on demand or automatically shut down an environment when you're done with it. You essentially end up with something like this. You take a bunch of VMs, and the job of Mesos, you can think about it as kind of the, it's a resource scheduler, right? It's a kernel or OS of this kind of a distributed system. And it takes VMs and treats them as a bunch of resources that it can now effectively manage. And then on top of Mesos, there will be Marathon, which is sort of a scheduler and process manager, can now take that set of VMs and now deploy processes, containers, and other things on top of that. And the end result is you would get a deployment topology of something like what you see on the right hand side. And that is, on top of that, the processes that are brought up and spun up are now your things like Kafka and Cassandra and Twitter feeds and that sort of stuff. Does that make sense? I know I'm going pretty fast, and there's not a whole lot of questions, but hopefully you have some questions. I'll finish in about 5 minutes, and then we could do a Q&A. So that's kind of the machinery, right? A little bit about what the pieces of the software stack is, a little bit about what the pieces of a DevOps stack is. Now let's have a little bit of fun with applications and some analytics that you can put together on top of systems like that. So to take it for a spin, I'll give you a real-time Twitter sentiment analytics for new movie reviews. We wrote this as a hello world analytics, but it quickly turned into something that is probably a bit too complex to really be considered hello world. And so we kind of think about it as a data science kitchen. And we have a series of blogs. We have, I think, 7 blog post series on Data Science Kitchen, where we document every step that data scientists would have to go through to essentially put up a sentiment analysis applications for the Twitter data. What it will do conceptually high level, it will get actual Twitter data through Twitter streaming APIs. It will apply necessary models to analyze the data in real time. So every second you actually see the new tweets coming in, and they're being sorted into positive, negative, and in various other things. And behind it, we expose all the things that make it work, which is the mathematical model, the training set, the dictionary, and the discussion for why those things were chosen for the reason they were chosen. When you have a choice of multiple dictionaries, how do you actually choose? Right? What is the impact of a good dictionary or a bad dictionary? What should be the right size of the training size? And what's the relationship between dictionaries and data sets and training models and things like that? And then we give you nice UI to then play with all that data coming back. That demo is running on AWS as a public service. Everything is open source and everything is documented. So just to give you a sense for what is it that you can do with the model is we monitor movies. And we try to have a nice mix of movies of 2016 and 2017 because it's fun to look at historic graphs. And it's fun to pick up some interesting events that happen over a long hold with some of the older movies and compare with same trends that are happening at the same time with the new movies. And sometimes you can pick up very interesting things, which are universally true of all movies. Something happens and everybody is chatting. And at other times, they're clearly chatting about one thing, but not chatting about other things. And the thing that you can't quite see, but the graph above is a real-time graph. You don't see it would say actually real-time sentiments versus historic sentiments. It's just hidden by the pop-up. But if you look at the timestamps, right? I was preparing the slides yesterday. So this is last night from 5:24 to 5:32, right? In a span of 6 minutes. This was the real data coming in and being classified. On this side, you could see the actual tweets coming. And you can click on the tweet and you'll see how it got scored, and the other way around. You can click on the scoring and it will bring up the feeds that populated that area. Sometimes it's fascinating to troubleshoot algorithms. You look at it, well, why was this positive or why was this negative? And there is limit to what machines can do today, of course, but this is it's just fun to play with. you can look at various ways in which data is presented. And one interesting point here is that we quickly realized that not all Twitter users are born equal when it comes to influence. We have some people who are much more important, and their opinions are much more important than others. Those tend to be the ones with more followers, right? So that analytics is then further applied to 3 segments, which are all the Twitter users with less than 500 followers, between 500 and 5,000, and then the mega users, mega influencers, those who have more than 5,000 people following them. And sometimes it's interesting when the trends align or not align, right? And finally, a couple of interesting anecdotes. So this is side-by-side comparison for the same time period of Star Wars and Suicide Squad. And you can very clearly see huge peaks, right, in the distribution. So the one in December is when Carrie Fisher died. And it was interesting that we see spike in both positive and negatives. That was kind of, puzzling me for a second. I thought, well, we'll see spike of negativity. Clearly, we see that. But there was also spike of positivity. And here's some examples of the positive and negative tweets. You could see that there's a lot of uplifting things. Sometimes they're really sad messages, but a lot of them are celebratory messages. People remembering the best about career, right, of the star that passed away. Now, there on the Suicide Squad, that's an Oscar night. But what's interesting is that Star Wars did not get the spike on the same night because they weren't up for any nominations. But they got a spike in January when they announced their new Star Wars movie, right? Next movie comes in, everybody's chatting about them. So it's obvious, but these are the kinds of things that are very clear on those graphs. And I'm done with my Kant presentation, but what I want to show you is, first of all, this is this little live demo that I was talking to you about. It's a teaching tool, so it's for fun. But we explain you a little bit what it is. We give you a bunch of different links to where to read more or where to go to deploy it. And then you can go and play with this stuff. And this is real time. As you can see, this, I don't know, 11:34. Yeah, I didn't refresh it. Yeah, in a long time. So there you go. It will take a second to restart, but you see historical is right there. This is now 1912, and we're gonna start seeing some, Doctor Strange, nobody is going there. We should go to Star Wars. And you could see, so this is one tweet, but then as more of them are starting to fall off, they're gonna start being scored, right? The last thing that I wanted to do today is show you just a little bit of our blog, because all of this is just a highlight, but in the blogs, we really put all the content where we document how all that stuff works under the cover. So for example, this is our blog, and we have series of blogs on big data, and some on search, and some on data sciences. We're starting to write about AI and chatbots and other fun things like that. But for example, under data sciences, we have this 7-post series on Data Science Kitchen, and it really starts with, why we're doing this, and then what is the scientist's key vocabulary and key scientific process. And then how do you understand structure of the data in Twitter strings enough to figure out what is the approach that you're going to take in creating these models. And after that, discussing, how do you construct data dictionary? Where do they come from? What constitutes good dictionary versus bad dictionary? How we ended up, we give you a list of dictionaries that we've selected here and justify and explain why. And then there is a special section on now creating training sets and training data and preparing the data for all of this. And then finally selecting model, training, and evaluating. I'll just click on one of them and show you that we do actually take you step by step. This is about models, how they work, how you evaluate them, what are the different mathematics behind it, and so forth. So that's in a nutshell what we do. And I'm done with my Kant content. And if you guys have any questions, I'll be happy to try to answer them. Yes, please.
So it sounds to me like Grid Dynamics makes money by doing projects
We're an engineering services company.
Do you keep any of your secret sauce unpublished?
So a lot of secret sauce doesn't belong to us. They belong to our customers. Those are their private IP. So that we'll never divulge. What we do as a matter of a business model, when we solve an interesting business problem with a customer, and we think that there is a reusable lessons there, we usually not required to perform lobotomy, right, as a result of performing this project. So we learned something. And so then it's an R&D that's done on our nickel and dime to then create the right blueprint with the right pieces of software and create it from scratch from learnings. I intend to, with some good luck and health, to publish a lot more. We just got started. We started the blueprint program last year. We published 2 or 3 blueprints last year. And we published 28 deep content blog posts last year. I hope to publish 100 this year. I hope to roll out at least half a dozen blueprints. And we'll see how it goes. But I hope to open up as much of these kinds of IP as I can, because that's frankly our main go-to-market plan. Be the good guys that write about stuff people want to hear about, and then after that, customers really need help anyways.
Okay, follow-up.
Yes?
What's so difficult with online learning is the delay in, I could train my model with new data coming in.
Mm-hmm.
Is the delay the fact that you want to vet the data before you feed it to the model? Is that the issue?
No, it really depends. I mean, it depends on what volumes of data. It depends on what structures are underneath. I'll give you an example, for example, from search. So you take standard Lucene Solr, and the way indexing works, typically work, you almost can't help it but to write it as a batch process. To try to update indexes live on the fly as, let's say, product availability changes is actually a very difficult thing to do in a core technology. Now, we happen to do a lot of work with Lucene and Solr, and so our engineers over the years rewrote half of Lucene core to allow it to do things like that, which we did donate back to the community, and actually we are core committers to, some of our engineers are core committers to Solr Lucene and pretty well known in the community for our contributions along these lines, for example, specifically. But it really depends on a lot of things, on how well you can adjust data structures on the fly, and indexes and other things. Yes?
DPoS?
Hmm?
I mean, the next step looks like, for you guys, we're thinking about DPoS based on the Mesos and Marathon stack.
Mm-hmm.
Thoughts so far? I mean, I know it's kind of early yet. But
I really don't know. We have a lot of ideas where to take it. And some of it is newest, greatest technology. Some of it is more integration points. Some of it going deeper in a domain. I'm very interested in deep learning as well as machine learning, and finding intersections around natural speech language processing that are bringing some of these best worlds together and trying to create a blueprint. Well, how do you actually do some of the applications which require those types of capabilities? Some of it is upgrading to maybe latest versions of something. One of the things we want to do is replace Redis with in-memory data grid, something like Apache Ignite, and so forth. Yes?
The free data stored in your different architecture, Redis, Cassandra, and HDFS.
Mm-hmm.
When do you recommend to store it Cassandra, and when do you recommend to store it?
So Cassandra for us is operational store. So when you need, there is a couple of use cases for that. One is when you need fairly complex data structures from your application domain. Let's even say catalog, right, and product data information, which is what you're going to be analyzing as you're making your decisions. You got to put it somewhere. You're probably going to put it in Cassandra. So it's a really good general purpose operational store. It's slow for some applications. Hence, you have something like in-memory data grid or something like Redis for lighter weight, faster access for simpler data. That's the reason why we have two. Although architects always have the best intentions, and then developers are always doing something else. So even our own engineers, with this nicely laid out difference between data stores, are starting to put things that logically would belong to Redis to Cassandra real fast. Why? It's easier to put everything in one place. And sometimes it's easier to integrate. For example, that particular demo where you have a real-time UI, while the framework that was used for real-time UI have native support of Cassandra. So it's really easy to dump the data in Cassandra and then visualize it, right, that way. You can drive Tableau from Cassandra. HDFS is usually for integration with other Hadoop-based systems.
You have Redis, so do you reference Redis when you write the sparse query?
Yeah, so Redis is there for lookup data. When you need really quickly to look up something, Redis is a natural choice.
And that really works in a big data environment when you have terabytes of data.
Reference data is usually small. Reference data is small, yeah. Maybe, black labeled IP addresses or some other things. Yes?
I have a question about the developer environment. You use so many different tools and languages to scale, but when I'm a developer, what I want to do, right, I want to make sure that whenever I deploy it, I don't make any mistakes. Right?
Yes.
I want to take it in, I want to test it as close
Yes.
to production. Am I installing all this stuff?
I'm very glad that you asked, because that's a point that I would gladly make. Actually, part of the reason why we like containerization, why we like Docker, and why we bother with all of this is because you need to basically take the same blueprint, but you need to scale it radically between developer environment and production. So actually exactly same architecture, but completely boiled down to the essentials, smallest number of containers possible that can be fired up in a tiny environment is part of the pipe of the deal.
So I do have a copy of production on my development computer, right? It's in tiny one.
Yep, well, usually, yeah, some subset or mask data or something like that.
And I can run like whole set of tests to make sure that
So the blueprint today gives you a little tiny environment on AWS. The reference architecture, the things that bake in there, it differentiates, bring this environment with a scaled down version, which brings small number of containers, but still on AWS. And then you can create a much more complex topology as it moves through your pipeline. The use case that you describe is a beautiful use case. It's actually yet another thing that we would love to do, to actually give you, Seryoja, you have something to say, get up.
Well, Uncommon. But when we were developing it, we actually just used compose on laptops and of course.
So it works, but we did not, today it's not documented as a part of the blueprint.
Yeah, but
So it works on a laptop.
I'll follow you up later.
Yeah, please do. Just follow up privately.
You already talked to me about it, but not about the development.
Okay. Okay, cool. I think we are running out of time, and you guys are running out of questions. Well, thank you very much for time and attention.
Awesome. Okay, and Jamie's beer showed up, right?
Yeah, did you think it was yesterday? Is that what you said? I think you guys are next. Can you hang out for a little bit, Jamie? Yeah, these guys are going. Yeah, congratulations on the baby, by the way. I haven't seen you since then. Oh, yeah. Screensaver. All right, so next up is the Apache Beam.
All right, so give us a few minutes to get ready here. I can kind of chat randomly while I do so.
Beer time.
Or actually, folks are going to get some beer and food and stuff.
Yeah,
That
sure.
sounds good.
We have water there or just beer?
There's water in the back.
Oh, thank you.
Go grab one.
You want one?
Yeah, sure. Grab me.
Yes, of course.
What was the primary reason for changing the cloud for within 6 months?
Just business. Customer, yeah, they went between Azure, IBM Software, and AWS in circles. Yeah. A lot of customers do that, like every single one of them. And if they pick the client, often they will pick Amazon and they hate the choice if they're a retailer. They want to